Hi, in this video, I'll be going through the idea of integration by building up the foundations through definite integrals first. So let's begin. So before we start with integration, let's understand how it came about, or not really how it came about, but let's understand why we want to do integration. So let's say we want to estimate an area. Then what we really want to do is, if we have a graph, and we don't know how to find the area under it, what mathematicians did in the past is they use rectangles to approximate the area. So you can take rectangles where the endpoint, where the rectangles start from the right and then you draw upwards. From the left, then you take this whole length from the function and you draw leftwards, like the following. So the endpoint is at the right. Or you can do it from the left, from this side, where you draw from inwards. And you can see you're overestimating it when you do it this way, and underestimating when you do it here. Because you're now drawing a rectangle inside the graph, and the other one is you're drawing from the outer side. Or you can even draw it where the point starts in the middle and then you just draw a graph from there, and then you see the estimation actually might get better. But if you realize, if you draw more rectangles, the estimation definitely gets better regardless, because now you have a lesser error bound. And so how did they estimate the area under a graph? Is that they draw many rectangles so that approximation is good enough to estimate it. And so we can see that as the number of rectangles increase to infinity, this area of the rectangles will approach the area of the graph. And that's really what we want to capture. The idea of taking a limit to infinity, and we take the sum of the areas, it will just be the area under the graph. And so what we can do when we want to estimate the area under a graph is we divide the interval into equal subintervals, and we construct rectangles by choosing sample points over here, and then we calculate the total area of the graph, and then we take the limit to infinity as n approaches infinity, and that will be the area under the graph. Mathematically, you can write it in this way, and then you choose sample points, and then you just compute this sum. And this sum is known as the Riemann sum, and the limit of this Riemann sum as n goes to infinity is the area under the graph. So we'll see an example to better understand it. For example, you'll find the area under the graph of y equals x squared from 0 to 1. Well, you divide the interval 0 to 1 into 0 over 1 over n all the way, and for each interval you choose you choose a sample point, for this, in this case, the right endpoint, and then now the area of one of these rectangles is I squared over n cubed, and so the total area is this, and you can rewrite it in this form. And if you just take out the 1 over n cubed because it's a constant, we just need to evaluate the sum of I squared, and this has a formula over here, and you can see this will be the formula of the total area with n rectangles. And so you just take the limit of this to infinity, and you see that it's 1/3. And this really captures the idea of how we want to estimate the area under a graph. And so mathematicians just created a better notation to capture it, and this is known as the definite integral. And so the limit of the Riemann sum as n approaches infinity will now can be written in a nicer way, where we write this sigma notation to represent the sum from a to b, fx is the function, and dx is like the small change in x. And this is known as the definite integral of f from a to b. And so the definite integral is defined to be the limit of the Riemann sum. And if this limit exists, then we say that f is integrable from a to b, because now this will equals to L. Some remarks is that the sample point chosen in the Riemann sum does not matter, and the width does not matter as well. It doesn't need to be the same, because when you take infinite number of rectangles, all the sample points, like you can just imagine your interval becoming super small, and it doesn't matter whether they are equal intervals or not, because all of them will be as small. And so this is like the notation. The b will be known as the upper limit, a is lower limit. The function you're integrating will be called the integrand, and x is the variable of integration. And really, now we want to learn how to evaluate such definite integrals, and we'll build our conceptual understanding. So, knowing that the definite integral is the limit of a sum, it gives us certain properties. We'll talk about the geometric ones first. So if you are a positive function, meaning your function always lies above the x-axis, it really represents the area under the graph, like what we have presented. And if you are not positive, meaning if you are non-positive, meaning you lie below the graph, below the x-axis, then it represents the negative area, because when you use the rectangles, each of this length is now negative f, is like a negative value, and so when you sum them all up, it still be negative, so it represents like negative area. So when you integrate a graph that cuts the x-axis at a certain point, really the graph, the area under this part will be positive and this part will be negative, so it's like a1 minus a2 and gives you the net area. So if you want to find total area, you just take the modulus. And more properties is that the integration of a constant function, like c, because it's like area, it's just c bracket b minus a. But that's of course the intuitive understanding. And if you want to prove it, it really just takes the sum, which equals to c times b minus a. And because this is not in terms of n, as n goes to infinity, this will still remain as c times b minus a. And so the integral of a constant function is c times b minus a. And then there will be a lot of properties that the definite integral satisfies, which can all be proven by limit laws, which we are familiarized with. So, if you integrate from b to a, is the same as integrating the negative of a to b. And if you integrate from a to a, then of course there's no area, so it's like 0, but you can prove it again using limit laws. And you see, all these laws are relatively straightforward to prove, and I'll just show you the proof of number 4 to show you how it's just proving the laws using limits. Because if you define the integral of a to b of fx plus gx, it is just the limit of a sum of now this, and you can break this up into the f portion and the g portion, and this is just the integral of f, and this is the integral of g. So it's just really playing around with the limit laws. And this gives us, now we'll move on to something more important, which is the fundamental theorem of calculus. And this is just the first part of the theorem. In subsequent videos, we'll show you the second part, but let's try to understand what is the fundamental theorem of calculus. It states that suppose f is continuous, and we define a new function which is the integral of x a to x of ft dt. Meaning you have a graph over here. So you have a graph so you start with a, then you calculate the area under to x, and then x has different, you can take x any point from a to b. Then each of these different x will give you a unique value because it's a limit. And so we say that this is a well-defined function. We can actually now prove that g is continuous, it's also differentiable, and its derivative is actually fx. And nicely, it gives us this formula. So fx will equals to the differentiation of a to x of ft dt. So this is the fundamental theorem of calculus, and I'll show you some users later on. So let's prove it first. So we just take a subinterval of a to b. We know that now, because it's a closed interval, it's continuous and differentiable. It's continuous. We have the extreme value theorem to show that there exist points where it takes the minimum and maximum value. And so when you integrate it, because we have this rule now over here, if fx is greater than gx, the integral of fx will be greater than the integral of gx. So when you integrate it over here, this one will still, the integral of this and this will be larger. But since these are constants, we just know it is the constant times the width of the interval h. And then you add gx to both sides, so that we get this. And we know this is, we apply the additive rule, it becomes gx plus h, because now this point will be integral of a to x plus h of ft dt. And so now we just take the limit as x approaches h from the right. All these will approach x plus as well, because the interval closes in. So fu will approach fx and fv will approach fx. By squeeze theorem, it just means that this left hand side limit, right hand side limit both approaches gx, and so by squeeze theorem, gx plus, the limit of gx plus h as h approaches 0 from the right is gx. And so g is continuous from the right, and so you can put a close bracket from the a side already. And you can similarly show that g is continuous from the left, and this closes the bracket on the right, on b. And so g is continuous on the closed interval a to b. In a very similar way, you want to prove that it's differentiable on the interior. You can just take gx plus h minus gx, and this will just be actually fx, because this is a to x plus h, and the other one is minus a to x, which is actually just plus x to a, so a to x plus h. So this thing will become integral of x plus h. So actually this part is fx, and then we know this part will be the integral of x to x plus h of fx dx. So it's bounded within the max and min times the width. Then you just divide it by h, take the limit, and by squeeze theorem, it will just be fx. And it's that simple to prove the fundamental theorem of calculus. And so you have now proven that the g prime of x equals to fx, because this is just g prime x and this is also g prime x. And hence, g is differentiable and its derivative is fx. And so we now see how we can use it. Because if we want to calculate the derivative of this function over here, then it's just square root of 1 plus x squared. So you just take this and then you just sub t as x. And then we can apply the chain rule to it as well to help us to get this. For example, if this is x4 instead of x, just x. And you can really see how the fundamental theorem links differentiation with integration. Because you have an integral, you differentiate to get the derivative, it's just back to the original function. So in some sense, there's now a very close link between differentiation and integration, and it's almost like reverses. And once we go through part 2 of fundamental theorem of calculus, we'll really show what it means to be a reverse. So you differentiate integral, you get back the same function. That's the idea for part 1. I've come to the end of this part of integration. There will be more to carry on, but it'll be too long for this video. So I'll catch you in the next one. Thank you.